Okay. So thank you for coming. What I'm going to do today is try to go over with you what we do at Mobileye, in the guts of Mobileye. How do we design the chip? Just a quick introduction to myself. As you can tell, I'm not from Israel originally. I made Aliyah in 1992 from Los Angeles. I went to UCLA, studied computer engineering, worked for several companies.
Newsflash. NASA.
Right. No, I mean, I worked for a few small companies, big companies. I worked for Jet Propulsion Laboratory, which was a subsidiary of NASA. Did image processing there. I worked for another company that we did this huge Star Wars project for the Air Force. Basically, what we call today Kipat Barzel, except this was to shoot missiles in space against the Russians, not little missiles against the Arabs. But the fact is that today it's much more difficult to get a missile out, that's being shot after 2 seconds instead of chasing it in space for a long time. In any case, I spent a lot of time doing image processing. When I came to Israel, I worked for IBM in Haifa, doing other kinds of design work, not necessarily image processing, and then worked for a small company called OptiBase in Herzliya. They were doing MPEG stuff, and then worked for NDS here, and then in 2000 I decided it was time to work for a startup. Worked for a small startup that went under with the 2000 bubble explosion, and I found myself on the streets, the worst point in my career, have no job, nothing, and the market is looking really ugly. Started looking for a job, and a friend of mine said, oh, well, Emmanuel, who used to work with us in NDS, so he's working for some automotive company in a house in Ramot. I said, oh, that sounds good. Automotive is not internet, so maybe there's more hope for that. In any case, that's where I started with Mobileye from the very beginning. We had, this idea of adaptive cruise control, nothing more than that, try to replace radar and provide some kind of simple, cheap solution based on a camera. And that's how we started with, basically 4 guys in the attic in Ramot designing the first EyeQ, and then until we've got to this day where we're working on autonomous vehicles, things have just sort of rolled. But so now what I would like to explain to you is what does it mean to design the EyeQ chip? What did we exactly do? And so I'll give you, I'm assuming that you know nothing about computer engineering, about electronic design, and so I'm going to give you sort of a background into that. If we take a look, this is the agenda that I'd like to go over. First, we'll go over some basics, talk about the difference between digital and analog, transistors and gates, combinational logic, sequential logic. Then we'll talk about how you turn that into actual chip design and what we do here, how we make the EyeQ. And then what you do with that chip afterwards, putting it on a board and integrating it in a system. And pretty much that's what I'd like to cover today.
You want to correct it, he's got wafers and chips.
Okay, yeah, I'll show you that in a minute. Okay, so now we'll do some basics. The first thing is that you could pretty much divide electronics into 2 giant fields. One is analog design and one is digital design. Just to give you an idea, analog is everything in the real world, a wave like this or a wave like this. The way you quantify it into digital is you basically turn each number into, or each segment of an analog wave or an analog field into something digital. You quantify it as a number. This is how you digitize the wave. This is how you would digitize the image. For those of you who don't recognize, this is me about 10 years ago.
We don't recognize.
Okay. Now the reason I bring all this up is that the EyeQ chip that we're designing also is divided into analog components and digital components. The fact is that all the design that's done here is digital, right? The only things that we do with analog is we have things like a PLL, which generates a clock, which is really the guts of the system. The whole system work. We have temperature sensors, voltage sensors, physical interfaces to video or to DRAM. All these things are blocks that we buy and integrate. We have to understand how they work. We have to make sure that they're appropriate for what we're doing, but we don't do analog design. We do digital design. And the digital design are things like CPUs, the actual brains of doing the calculations. We have these things called accelerators, which are our special sort of proprietary CPUs, which do image processing stuff, and that's really the core of Mobileye's uniqueness is that you can buy CPUs that do all kinds of general things, but we design them specifically to do the kinds of image processing that we need to do. And so they work very fast and very efficiently. All kinds of other different blocks in the chip that we'll look at in a minute. Okay. So now, once you get down to digital logic, so digital logic is basically broken up also into two areas. The first one is combinatorial, and the next one is sequential. Okay. So what does that mean? Combinatorial logic basically means that you're putting together logic, and you're not worried about time. Okay. So this page gives you an example of how would you do an adder. How do you add two numbers in computers? Okay. So for example, here, this is what's called a truth table. Okay, and the truth table of an adder says, okay, you have two numbers that you want to add. Okay, and the numbers were in the digital world. So in digital, there's either 0 or 1. Right? Okay, so now if we're going to add two numbers, you can also have a carry-in bit because you want to add more than just one number, so you have to bring another number in. So basically, you're adding 3 bits. So what would be adding 3 bits? If they're all 0, so the sum is 0, right? If one of them is 1, so the sum is 1, okay? And if two of them are 1, so the sum is actually 0, but you carry out. You bring that, it's just like carrying over, right? 9 plus 1 is 0, and then you bring 1 to the next column. So this is the carry out bit. So you have 1 plus 1, it's 0. It's like 9 plus 1. And then you carry out the next digit.
Binary.
It's in binary, okay? Fine. And then if you had 3 ones, so it would be that the sum would be 1 and you would carry out 1 to the next level. Okay, so this is basically the truth table of how you would add two numbers or really 3 bits in computers or in binary. So far we haven't even gotten into how do you do that in computers, okay? So now, the way you do that in computers, you need to be able to have a way to make these combinations. Okay, so now there's things called logic gates. Okay, now these are logic gates, and what they do is they do things. This is called exclusive OR. This is called an AND. This is called an OR. For example, okay, we take this what's called a NAND gate. It says that if you have two numbers that are 0, you'll put a 1 here. If either one of these is a 1, if either one of these is a 0, you get a 1. Only if you have 1 and 1, so you get a 0. Are you with me?
No.
Okay.
No, I think it's too much. It's a bit of too much.
Okay. So, okay, we'll try to bring it down, okay?
Let's do less numbers and more concepts.
That's the basic of a computer.
Right.
Yeah, we don't do numbers.
So at the fundamental level of a computer is basically this, what's called a NAND gate. I mean, you understand what an AND is. This and this, then we give you this number, okay? So only if you have a 1 and a 1, we give you a 0. Otherwise, if you don't have this and this, so then we give you a 1.
How do you distinguish between two things that are 1 but have different combinations? Like here you have multiple things that add up to 1.
Okay, so I'll show you that. So now, first of all, you have to understand how to put together 2 numbers. Then you can get into putting together 3 numbers and more. Okay, but right now, so I mean, this is basically how you do it with 3 numbers. This is the implementation of this. Okay, you basically need these few gates. Okay, and this is the A, B, and this carry in, the sum, and the carry out. Okay, so what I'm showing you right now is basically this AND gate. Okay, 1 gate. How do you do that? So one gate says that, which is an AND. Okay, the AND basically means that if both of these are 1, so we'll put a 1 here. This diagram is for a NAND, which is basically inverts the output. Okay, fine. So now, that's very nice. We're still at the level of extraction of logic. Okay, we still didn't make this electronics. Okay, so how do you make this in electronics? You need what's called a transistor. At the heart of all digital design is a transistor. A transistor is a very simple thing. It's a switch. It goes on and it goes off. Okay? So now what happens is that if you put some voltage, if you put a 1 here, okay? So now the switch is on and it connects the 2 other sides. Okay? If you put a 0 here, so this is open, there's nothing connected. Okay? So now what can you do with a switch like this? basically everything. This is how you design computers, okay? So now this is what we did here is you put one switch in series with another switch, and now this is basically the implementation of this NAND gate. How does it work? So here this is the voltage, it's 1. All right, so right now, if this is open and this is open, so this is like nothing exists here, so the 1 goes here, you get a 1. Okay? So now if either one of these is 0,
It's shorted.
if either one of them is 0, it's open. If this is open, so now this gets a 1. If this is closed, so it comes here, and it sees this is open, so there's nothing connecting it to ground, to 0. Only if you put a 1 here, close this, a 1 here, close this, so now this wire is connected straight to ground to 0. So if you get a 1 and a 1, you will get a 0. If you don't have a 1 and a 1, either of these are 0, the wire is never connected to ground, and it remains pulled up to 1, and you get a 1. So this is how we implement what's called a NAND gate. All computers are designed this way. You can design an entire machine, the most complicated thing, it's all based on this NAND.
Many of these. So
Okay? That's what computers are. There's nothing more to it but than a NAND gate. Now, it's true there are exclusive ORs, there's all kinds of different gates, but you can actually implement all the types of gates using NAND gates. Okay? Now, you can do other things. For example, you can make an OR gate. What's an OR gate? Either this is 1 or this is 1, right? So you can put this over here. And so now, if this is 1, it'll go to 0. If this side is 1, it'll go to 0. So either one will do it. You implement a different logic function. But at the end of the day, you can basically, all you need is a couple of transistors and you can make a computer. You can implement any type of logic. Okay? So now, in the old days, to design a computer, you would actually draw these things and you would buy, a chip that had these gates, okay? Or you would wire up transistors. Now, for already many decades, that we're using what's called high-level language, okay? This is called RTL, or Register Transfer Language, okay? It's basically the language of how to implement this, and there's code that there's a synthesizer, a compiler and a synthesizer that basically takes the code and translates it to gates and to transistors, and that's how the chip is actually made. But we, working here, basically design on this level of extraction. So for example, here it says the sum is A exclusive OR, B exclusive OR, carry, the carry out is this. And so this is how we would design. We don't design gates, we don't touch transistors. This is how the design is done today everywhere. Okay, so now that's just to make sort of the logic, but then you have to work in time. Okay, you have to be able to understand how
What's the language you're using?
Okay, so we're using Verilog.
Verilog.
But there's basically Verilog or VHDL are the two main languages. Okay, so now
That's the lowest level we're using, right?
Correct. Right. And so now the next step is sequential logic. I mean, if you wanted to make an adder, so you added a number, but now you want to add another number. So how do you do that? You have to have saved the first number that you added, and now you want to put in a new number. Okay, so that's called an accumulator, and we have tons of those. You have to be able to do things like that. You have to be able to save what you calculated and now use it at another stage.
You mean for it not to change?
Yes, exactly. So like let's say I added, 1 plus 1 is 2, and now I want to add 5 to that. Well, I have to have saved that 2 somewhere in time, in a memory element, and now bring in the 5 into my adder. If I just had an adder and I put 1, 1, 5, so now the 2 is gone, and now it's just 5 plus 1, right? And I want to do 5 plus 2. Okay, so you need what's called a memory element, and that's what we call sequential logic because it works in sequence, in time. Okay? And the way that's done is we have an element here, it's called a flip-flop. Okay? The flip-flop is the most basic memory element that you can have. If you take a whole bunch of flip-flops, so you call it a register, and you save many bits at one time. Okay, so now the flip-flop works basically again. You can implement it using NAND gates. This has these feedbacks here, and it saves the number that was put in whenever a clock comes. When the clock comes high, so now this gate basically transfers the data here, If the clock doesn't come, so now the data that was here is now saved here, and this can go crazy. This information is saved. Okay. So now this is how, for example, with our adder. So you have this clock running, and every time that the clock goes up, so now it's going to look at what was in A, B, and C, and it will see the sum, and it will put it at the output. So what we're trying to do, again, is save the information so that we can use it again. So now this is what I showed you here as an accumulator. Let's say that this combinational logic is the adder that we saw before. So now the inputs are those A, B, C. It adds a number. A clock comes here and says, okay, save that number. Now the number's saved. We feed it back here. Now the new number can be added in. And on the next clock, it saves the output and puts it here. Okay? So now, why is this important? So when you talk about, oh, our system, I've just bought a computer, it works at 200 megahertz, it works at 1 gigahertz. What does that matter, right? It's the speed of the clock, how fast the clock goes. That's how fast you can actually do any calculations, okay? The faster that you can run a clock through the system, so the faster you can make all kinds of calculations. There's a limiting factor, however. That's nice. So let's say we can run a clock through here at 100 megahertz. Okay, 100 megahertz means that every 10 nanoseconds you're going to have a clock. Okay, but what if all this logic, it takes time. For those transistors to open and close, it takes time. If we look back at this picture, so let's say, what if this takes 1 nanosecond, and this takes 1 nanosecond? Well, that's okay, so that means it takes 2 nanoseconds to go through here. But now here, we have a path that takes 1 gate, 2 gates, 3 gates. So really, it's taking 3 nanoseconds. And then we didn't take into account the wires actually have time delay. Okay? And if they're going very far across the chip, so now you have to have a driver so that the signal doesn't die away. Everything starts taking up time. So now, if we look at this picture again, okay, all this combinational logic takes more than 10 nanoseconds, so we can't put a clock of 100 megahertz here. We'll have to use a slower clock, right? So that's how the system is limited. Of course, we can play games, and we do play games, that in case, let's say that this really took more than 10 nanoseconds, what we can do is we can cut the logic and we can pipeline it. Okay, this is a little bit complicated, but what we do is we can do half of the logic first and then do half of the logic afterwards. Okay? And so it'll take 2 cycles the first time through, but after that it's all going in at one at a time. It's called pipelining. You follow? So you can do all kinds of tricks, but that's the difficulty of digital design, is you have to try to figure out how to do lots of calculations very fast. If you know the story of Mobileye, Amnon Shashua was given the task of trying to prove the idea that he can track images. And so he took, you can see them over here, he took 9 power PCs and hooked it up to a big video camera, and he proved that he can track images at something like 1 frame a second. 1 frame a second is not able to do anything in real time, right? We can't put on the brakes or do anything with such a slow system. But he proved that the concept works. Now he's just got to be able to make that thing work 30 frames a second. Our system's working at 60 frames a second. And also, we don't have, the luxury of putting 9 power PCs in a giant video camera. It's all got to be in a chip. And so that's why, myself and Emmanuel and a couple other guys came, and we learned the algorithm, and we built hardware specifically to do those algorithms so that it will work at 60 frames a second. Okay, so that's the work that we've done here. Okay, so now there's one other interesting thing when you're doing digital design, and that's there's actually an analog part of digital design. You see, the digital signals, even if we say, okay, all we're working with is 0 and 1 and 0, we're working with these straight line signals like we saw before. Everything's either 0 or 1, 0 or 1. The gate is open or the gate is closed. The fact of the matter is that there's nothing like 0 and 1. I mean, there's a voltage that slowly begins to ramp up until it gets to a certain level. And so at this point, we say, anything above here is considered 1. Anything below here, we don't know what it is. Anything over here is considered 0. So now, this is another thing that affects the speed of how you can work. Because if it takes you a long time to ramp up till you going from 0 to 1, so you have to wait that time. And so if we talked about the delay of going through gates, you also have the delay of how fast the signal goes up. And so all these things take time. And so all this is called is slew rate. How fast can the signal go up? In the old days, digital design used to work like this. You had 0 was 0 volts, and 1 was 5 volts. Okay? Or basically here, 5 volts, and then 10% of that was considered a 1. Okay? Today, inside our chip, I mean, things drop down to 3.3 volts, and now we're actually working inside the EyeQ at 1.1 volt. Okay? Which means you have a very small bandwidth, so we can go up very quickly. But you also have then a big problem of noise, because let's say that this is the noise on a 5 volt signal, so you still have 4 volts till you get to here. But if the whole noise is 1 volt and your whole signal is 1 volt, so now you don't see anything but noise, right? So there has to be very resistant to noise. You have to be, very careful about how everything is implemented when you're working with very low voltages. Okay, so that's just another piece of information of digital design. Okay, so now we'll go to the chip design. Okay, so now what is the process of designing a chip? First of all, you have to write a specification. And this, I have this little laughing man here because everybody thinks it's, oh, you don't need to write a specification, we just need to design. We know how to design, tell me what you want, and we start typing code. But the fact of the matter is that you can't do work like that. You have to, first and foremost, you have to write down what it is that you're going to do. And when you're writing it down, you realize that you didn't even understand what you were going to do or how you're going to do it. So
what do you want the chip to be able to do?
Excuse me?
You have to have it specified what?
You specify, okay, I want to add 2 numbers, okay? And these 2 numbers, well, how many bits are going to be there? How fast is it going to work? I want to make an accumulator. How does that work? Okay, so like, for example, when I started here, so I designed the tracker. The tracker is the block that basically follows image after image, okay? And there's many, many algorithmic pieces to it. I had to sit with different algorithms, guys, and say, okay, how do you do this? How do you do that? I drew up. There was no specification from the algorithms people, so I sat with people like Andrej, and he explained to me how it works, and then I drew a whole flow chart of this is how I think what you mean to say. He corrected me, no, this has to be like this, has to be like that, and so you have a specification of what you're going to do. At the end, he saw it, and he said, yeah, this is what I said, but it's wrong. And he realized that he needed to fix something in his algorithm because of how everything was documented. So the first thing you need to do is you need to make a specification that people can look at and say, yeah, that's what we want to make. Okay? After that, there are 2 parts of chip design. There's what we call the front end and what we call the back end. All right? The front end is what we do here at Mobileye. It's what most design houses in this country and everywhere do. The back end is more about physics and making the actual chip. The front end is about, you have a great idea. I want to make autonomous vehicles. Okay? So you have an idea, you make some algorithms, and you get some guys to design it in a chip. That's the front end. You do what we said RTL coding, which is in Verilog or VHDL, what we saw. You write the code. You do simulations, this is the output of the simulations. So whatever, there's all kinds of signals that you see, and then you can find, oh, this is the wrong number we were trying to get, and so you go back and you start doing debugging. Okay? So you do the simulations. After that, you do what's called IP integration. As I mentioned before, there are things that we design here. There are things that we buy from people. We're buying the CPUs from MIPS, for example. We have to wire all those up into our system. We buy the PLLs, the clocks, the temperature sensors from ST. All those things need to be put in place and integrated. Integrated means you don't just put it there and it works, right? You have to wire it up. You need to make sure that it's getting what it wants when it wants, everything, the timing works. So this is a whole integration process. Then you do what's called synthesis. And synthesis, as I mentioned, takes all your RTL code and it translates it into all those gates. Okay, it translates it into
What is
transistor.
RTL code?
R-
Stands for what?
RTL stands for Register Transfer Logic, because basically you could say that all of computers are what I showed you before, that accumulator where you have some logic that goes into a flip-flop, into a register, and that goes into some logic, into a register. And so all of digital design is known as basically RTL, as Register Transfer Logic, or RTL is also known as Register Transfer Language. Okay. So now, once you synthesize it, now this changes everything, and things may stop working. Why? Because, like I said before, you designed an adder, and you put it in, going into a register, and if there's no synthesis, that means it's not taking into account all the timing it takes 1 nanosecond to go through here, and the wire takes this long, and the signal takes this long to go up and down. All those things are not written here. All this says is, make me 1 plus 1. Okay? So yeah, 1 plus 1 works, you check that it makes 2 and you're good, right? But once you synthesize it, it could be you put a 1 gigahertz clock and it's not ready, right? And so now 1 plus 1, it sees 1 is 1, but the other, well, the signal didn't come up, it's 0. So 1 plus 1 is 0. I mean, 1 plus 1 is 1. What happened? Okay? So now you have what's called gate level, or net list, okay? And this net list has all the timing, it takes into account all of the physical properties, and so now you have to go back and say, whoa, we made this multiplier and it takes too long, we have to figure out, we'll make 2 multipliers, we'll have to do something faster, something else, okay? Or we have to say, no, sometimes we have to slow down the clock, there's nothing to do, okay? The VMP was supposed to work at 1 gigahertz, it now works at 800 megahertz, nothing to do, okay? So now that's the front end, and that's everything that we do here. But then you get to the back end, and we're using ST Microelectronics to do our back end stuff. So the back end, basically the first thing that they do is called design for test insertion. They put in all kinds of elements to make sure that when they produce the chip, it works. Okay, they need to be able to test everything. So they don't just run all of a scenario of Mobileye, tracking images or something. They need to be able to check each element quickly and see that it works. So they put in all kinds of things. The simplest thing to explain is a memory BIST, which basically you have a memory. How do you make sure that the memory works? You write numbers. You write a number, read it back. Is it the right one? Write, read. You write all kinds of different patterns to make sure that the memory works. So they insert all those kinds of things into the chip. Then they do another synthesis because of all the new logic. They also do place and route. So before we said, okay, we do synthesis, it translates it into gates. But we never said, hey, the MIPS is over here in this corner, and it's talking to this I2C peripheral over in this corner. It takes time, okay, to get there. So now you have to take into account how long the data takes to transfer. It may be talking to a CAN interface over here, so it's very fast. And so that's fine. But so all the timing that's related to place and route also comes into play, and we have a new gate list. Then you do simulations. You do what's called STA, static timing analysis. Static timing analysis is a tool that mathematically looks at all the wires, all the connections, and says, this wire takes 11 nanoseconds to get over here. Your 100 megahertz clock isn't going to work. Okay, it looks at everything mathematically. You don't run simulations, you just run an analysis on the whole design. And then finally do what's called formal verification. What happens, we just ran this synthesis tool. We ran another place and route and synthesis again. This changes our design. So now there's a special tool that compares and says, okay, this design that you made here, is it the same as the one that you intended before? Maybe something got messed up with all these translations. Maybe the tool inserted something by accident. Maybe it erased something. We're talking about millions of dollars. You can't make a mistake. If you need to fix a chip, you're going to have to spend millions of dollars again. So you have to check everything, even that the tools didn't make a mistake. So you have a comparison from here to here, you have a comparison from here to here. You make sure that everything has been done to make sure that we didn't make any mistakes.
Where is the back end then?
So all of this is done at ST. I mean, they have different places like in India, in Noida, in Crolles in France. I mean, ST has a lot of plants.
Is this sequential?
More or less. The fact is, I mean, it's a good question. Basically, we have what's called, there's a thing that's called 50% net list. And so once we have 50% net list means that basically the main blocks are all in place, things are all wired up. It hasn't been debugged, there could be lots of bugs, but the main elements are in place. So that already gives them a chance to do a run. And they can go through and see, okay, where's the initial placement? It could be that we may need to move one block here or there, but in general, we know we have our video inputs, we have our peripherals, we have our MIPS, we have the interconnect, the DRAM interface, all the things are in place. And so, yes, you're right, they're able to actually do a run already, okay? And right, while there's still designers doing coding, there's another guy who's running the synthesis and saying, your design is not going to work as fast as you thought. You better start thinking about fixing it. So there are definitely loops going on here.
But the loops you explained were loops between the front end and the back end. Is there loops where ST come back and say, this design isn't right, or it's failed here, you guys need to redo, or?
Yeah, definitely. I mean, like I said, so let's say we're coding, and then we got 50% done. That means there's another 50% of serious design work that needs to be done. They're already started doing place and route, and they could say, you're going to need to use a bigger chip. You have way too much logic here. Or, you're going to need to eliminate something to make it closer. Or we need to think about a different type of technology to put this in. Or we need more pins, or I don't know what. There are things that can come up. I mean, the pins probably not, because that's pretty simple. But in terms of the synthesis and the timing that's going on, in terms of the place and route and how that affects the timing and how that affects the whole chip and the possibility of routing, all that information already comes with netlist pass 50%. Then we also have a netlist pass of 90%, where we're saying just little bug fixes, but so you can start working, seriously doing your back end job.
Can I ask a few questions? Yeah. Now, when we design here, basically we don't do physical design. You don't take NAND gates and AND gates and put them together. You design blocks.
No, we do logic design. We do, like I said, I mean, it's on the level of RTL, of Verilog coding. But yeah, we say this, I need this, and it needs to go to...
As blocks. As PLL and
No. The VMP, the MPC, the PMA, the video interface, all of that stuff is designed bare bones, from scratch, zero.
As a circuit?
Yeah, like when I design, for example, I'll give you an example. To compare two images, all right? Okay. What you need to do is you need to take the two images and you look at them and you want to say, are we tracking the same car? Okay? So what you need to do is you need to take the images, make sure that they're all the same size, and then you start going, this pixel minus this pixel, if it's 0. This pixel minus this pixel is 0. So we start going through and we do a subtraction of each pixel. Okay, we do what's called SSD. SSD is sum squared difference. You take the difference of every pixel in the image, okay? You sum it, and then you square it, okay? So you add the whole thing, and at the end you get one number. If that number is 0, so, I'm looking at the same image. If that number is, 1,000, so you lost track of the thing. What if it's like 100, or what if it's 20? So you define a certain threshold that it's close enough, we're still tracking the same image, okay? So now, how do you do that? So I wrote code that says, take pixel A, take pixel B, minus this, exactly in code.
As a code?
Yeah.
As a code, as an assembly language?
It's called the RTL language, yeah. It's like, yeah. It's called, I mean, at the end of the day, it's like putting gates together, okay?
Yeah, but not physically.
Physically.
Otherwise, why you need a language to design? Why you need the software to design?
No, so the software, there's no software. There's the language, okay, which describes what it's going to do. It's going to do A minus B. Okay, then the synthesizer basically takes that and translates A minus B into those transistors,
Gates,
into
yes.
those gates, okay? And then at the end of the day, there's a gate level, there's a net list, and then that translates into masks, which I'll show you now.
Right, so the back end, like in the nest, is abroad and the front end stuff is here?
Yeah.
The last question is, what's the difference between Mobileye chip, EyeQ, and a generic ARM?
Oh, so that's exactly the next slide. All right. So now this is the EyeQ. In general, I mean, this is the architecture for EyeQ 4. Okay, EyeQ 1, 2, and 3 are very similar. Basically, you have these store-bought CPUs. Okay, so here in EyeQ 4 we have MIPS. Basically, we've been using MIPS for EyeQ 2, 3, and 4. EyeQ 1 was based on ARM processors. These are general processors that you can do things like adding numbers, subtracting, multiply, move, store, things, basic instructions. Okay. But this is not enough for us to be able to do what we do at 60 frames a second, okay? Now, what we design in Mobileye is, like I said, this is what makes Mobileye unique, and this is why people are still trying to compete with us, okay? These are what we call accelerators. They're basically very specific image processing CPUs, okay? And they do, like, for example, I said that we need to do sum squared difference. We need to compare two images. Okay, if you have to do that with a regular CPU, that means you have to say, okay, the images, we have this DRAM interface. The memory is all stored off. It's very expensive to make a memory inside your chip. You buy memories, okay? The video comes in through here from a camera, right? It goes through this interconnect, which basically connects all the blocks, and it's stored in some RAM off of the chip, okay? When you want to, now let's say somebody said, compare two images. So now what you have to do is you have to say, okay, image 1 is over here. Please read that pixel, bring it over here, now I save it. Oh, you want the other pixel? Okay, go over here and get the pixel from the image number 2, bring it over here. Okay, now I need to take